Knots are fundamental to all life. The DNA inside our bodies are twisted up loops, tangled in knots, and the only way for our bodies to use that DNA is to change the type of knot. Different knots also provide different properties to materials that we use every day. So in order to understand this important aspect in all our lives, we must first answer the most important question in the branch of math known as knot theory. How do I tell this knot from that knot? In knot theory, a knot is a normal knot tied in a rope, but with the ends tied together like this. Here are two of the most basic knots, the trefoil and the unknot. Knots are classified based on the simplest number of crossings in the rope. To check if two knots are the same, there are three moves that you can use. The twist, just twisting a loop, the poke, poking a rope out from under another, and the slide, sliding a crossing across a rope. These moves are known as the Reidemeister moves. One strategy that you can use to verify two knots are the same is trial and error with Reidemeister moves, but after a couple hundred moves, it's going to be pretty tempting to just say that these two knots are different. Luckily for you though, there is a max number of moves that you can try before deciding that they aren't equal. Unluckily though, that number is 236 times n to the power of 11. Because that's such a big number even for small knots, mathematicians use a different strategy where they examine knot invariance, properties of the knots that don't change with Reidemeister moves. If two knots have different invariance, then no amount of Reidemeister moves will make them equal. One of these invariants is tricolorability, where each crossing must either have three colors or all the same colors. As you can see, the unknot is uncolorable, but the trefoil is tricolorable. But how do you tell two uncolorable knots apart? You can use another invariant such as the Jones polynomial. Where this really comes in handy though is examining how enzymes in our DNA break apart knots, because bacteria uses a similar strategy to reproduce. Most common antibiotics work by inhibiting these knot tying enzymes. Some chemotherapies also inhibit these enzymes in cancerous cells, stopping the spread. Tying molecules into different knots has also catapulted material science into a new age where many new properties are possible. Thanks for unraveling some facts about knots with me.